Hello everybody, this is Justin Polite. I'm in Kendall Jacobs' Math 1100 and 1400 class. Today we're going to be working on a seminar, and this one is called Addition and Subtraction, Algorithms and Manipulatives. We're going to try to cover as much detail as we can throughout all these problems. We're using mixed reality portal in order to create this video, and basically we're just going to go underway. So first problem is 67 plus 67 base 8 plus 2, 4 base 8. So we're just going to go ahead and bring this up here real quick. So we have 6, 7 plus 2, 4 base 8. And we're going to kind of understand this a little bit. So I have written here what our ones place is, what our tens place is. And I also did a base block right here. So what we do is, in order to do in order to add this like normal we would do, I did this a little bit different. I did it horizontally, but if we want to do 7 plus 4, because we want to start right from left, if we want to do 7 plus 4, we get 11. But we're in base 8, and we're not in base 10. So what we do is 8 being our top number. So basically we can understand this like over here. If we're using base blocks, this would actually in base 10 equal 10, but in base 8 it equals 8. And all these individual ones right here, these small ones, 8 of them would equal one of these longs. Whereas in base 10 in regular, 10 of these small ones would equal one of these longs. So basically what we do is 7 plus 4 is 11, so we can get 1 8 out of that 11 and have 3 left over. So what that means is we'll put 1 above 6. We could put 1 above 6, and then what we would do is we would leave the 3 left over right here. So what we do is we go on to the tens place right here, right? So this is the ones, this is the tens. So we do 6 plus 2 plus the 1 that we put right here, the 1 8. So that's 6 plus 1 is 7 plus 2 is 9. So out of 9 we can get 1 8, so we put 1 8, and then we can get 1 left over from that 8, so we put 1 right there. In order to draw this in a base block representation, what we do is we draw these longs, and I explained earlier that the longs actually equal stacks of 8, and then these are just ones. So basically this is supposed to represent 6 and 7 and 2 and 4. And what we do is we just add them like we normally would. And our answer comes out to being 113 base 8. And this is supposed to resemble a flat. So in base 8, a flat would equal 80. And so that's what we have right here. So let's go on to another problem here. I think it'd be this one right here. I don't want to do this one yet, sorry. Let me do this lattice one real quick. So in lattice addition, that same problem that we're working on, we know that 7 plus 4 is 11, right? So, and then base 8, we get 1 8 and 3 left over. So in order to write that in lattice addition, because we're doing this exactly the same way that we did additive, except we draw a rectangle, and then we divide it in half and make 2 squares. And then we go ahead and do horizontal cuts in the individual squares. So we have slots for 4 different digits. So basically what we do is 7 plus 4 is 11. We get 1 8 out of that 11, and we get 3 left over. And that's how we write it over here. This is the 1 side, this is the 10 side. Then we have 6 plus that 1 8 gives us 7 plus 2 is 9, so we get 1 8 and 1 left over. And in order to add this, we do cross-diagonal multiplication. So 3, there's nothing in this 3 slot except for 3. 1 and 1 is 1, and 1 is 1. So basically we just go in a diagonal, and then we write down the multiplication answers to those down below. So 3, 1, and 1 is 113 base 8. So then, excuse me, now we'll go into a hexadecimal number real quick. And so what this is right here is we also have letters in our numbers, and these letters actually end up being numbers. So A is equal to 10, B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14, F is equal to 15. And so what we do is